Hello, welcome to another problem session. So here is a really nice problem from a very good book on mechanics. I would recommend this book, Kleppner and Cole and Co. Okay, so you can pause this video and try to solve it yourself, and then come back to my solution. So I'll give you a moment to do that. All right, so here you go. All right, here we go now. So in this problem, what's going on is everything is frictionless. So first thing to notice is everything is frictionless. And the speeds are not very high, so also ignore air resistance. So, which means energy will be conserved. Energy of the block, for instance, will be conserved. And that will be one of the things we can use. And the question turns out to be, it's given that at this point, when this block is going this way, it's pushing against the track, and that force is equal to weight. Okay, so that is given. This is given, and using that information and other physics things you can set up here, we're supposed to find this. All right, so already know that this height will translate into that speed, right? And this speed we don't know yet, but then between, say, point, this is some t0 and this is some time t, this time t0. So energy conservation will give me one equation. So let's write that down and see if we can get z from there itself, or do we need something more? So energy conservation is really not that difficult to write down. So over here the V is 0, so 0 kinetic energy. So energy at t equal to energy at t0. So this one is 0 kinetic energy, and potential energy, if I take this is this level as 0 of potential energy, we just choose this. We choose this because z is with respect to that. So this is mz, and because z is above that, I have a positive. So z is greater than 0 here in my reference. And in some sense, you can say this is my z-axis or something like that. Over here, at this point, the height is 2r. So this height is 2r. So, and we assume the speed is v. So you got half mv square plus mg times 2 times r. Okay. 2 times r. You can see here m just got cancelled out from everything, but in this equation this r is supposed to be given to us. Okay, this r is given, this r is given, so z will be in terms of r as answer. So we can think of we have let's look at what we don't know. We don't know this and we don't know this. So this is one equation, but we need one more to determine that. And that's the equation for F equals ma. That's the equation in which we're going to make use of this force. So second equation, using information at P, and that's it's a circular motion. It's going in a circle. So at this point, you're going to have acceleration this way is v square over r, and there are no forces in that direction, so tangential acceleration will be actually 0. No forces in that direction, because the forces, if you look at the forces, there's one gravity this way, and then there is a normal this way or that way. We have to decide which way is the normal. So the way it says pushes against the top of the track. So if the block is pushing, if the block is pushing into it, then the normal will be this way. So this is the F. F is a block pushing on the track upward, and this N is the reaction to it, reaction to this push, hence downward. So that's not how this is a normal, and its value is F, which is equal to W. Normal, this is the magnitude wise. So it turns out at this point, a free body diagram will tell me there are two forces, weight and one more weight, normal, which is equal to weight. So together, pointed down, acceleration is AC. So I've got 2 times weight equals to mv square over r, and the weight is mg. So m got cancelled out. So I got a v square over 2. I need v square over 2 in here, so I'm just going to use v square over 2. So v square over 2 from here, bringing 2 down here, gr. So this is equal to gr. So this is equation number 2. Okay. So I've got 1 and 2, from 1 and 2, from 1 and 2, 1 and 2. If I put this here, I get gr here, 2gr equal gz. So gr plus 2gr equals zz, and of course g all got cancelled out from, so z equals to 3r. So that's the answer. Okay, let's go back and re-examine what we did. So first thing was to understand that we can very easily get energy conservation between this instance and this instance. So that was very easy to get, right? However, there were 2 unknowns here, and you need to get one more equation. And the second one was what's going on when the block is moving around here, how the forces are playing. So the way it is worded here is block is pushing against the track, not just gliding by, but actually pushing with a force equal to its own weight. That means the track will push back. So the track will push back downward. track will push back on it like that. Force from track. And that's what the normal force, which is normal force. And so once we recognize this, is actually the main point you have to recognize. Otherwise you will get, suppose I had made a mistake and I thought the normal was up, then weight down. So mistake will be like this. Weight is down and normal is up, which is equal to weight of this, and then net will be zero force on block. So if you have a zero force, if this side is zero, then v square bar will be zero, so v square will be zero. And then z will be zero, which kind of makes no sense. If I start from here, how does it go over there? I start at rest over here, how did it go there? There's no, it's a problem, it's fallacy. So this turns out to be an important set of arguments I made. Maybe you want to go back and review more of this argument, think about it more, talk to your friends, talk to your teacher. Okay, so I think this is a good problem. I'm going to stop here. Don't forget to subscribe to this channel if you like it. There will be more problems like this coming up on this channel. I'll be doing it throughout the year. And there will be mechanics, thermodynamics, fluids, electricity and magnetism, optics. We're going to just build up the whole set of introductory physics problems. Okay, so we'll talk to you later. Bye.